All right. Good day, everyone. I hope you're all keeping well. Couple of reminders and announcements. The Chapter 5 and 6 assignments are due tonight. So that includes the homework, the quiz, and the lab. Those are all due by midnight tonight. So one thing we're going to do today is I'll open it up and you guys can ask any questions that you guys have about anything on those assignments. Just remember they are due tonight. The Chapter 7 assignments are currently due for next Tuesday, so you have all weekend to do them. And when we meet up on Tuesday, you'll be able to ask any questions you have then. As a reminder, we are on track to resume regular operations next week. So all things normal, we will have lecture as normal next week. If a student still can't be there in person or just is exercising and wow, already thirsty. If a student can't or doesn't wish to be present in class, then the lectures will still be recorded. You can still catch up on all the material, but we will have in-person meetings again. Good day, good day. Welcome, welcome. So Chapter 5 and 6 assignments are due tonight. Chapter 7 assignments are due next Tuesday, where we will resume meeting as normal. Today we're going to finish Chapter 7 and be aware that the next test is coming up in a couple of weeks. If I was to give a tentative date for that test, it would be around October the 4th, which is in 2 weeks. Today we're gonna. I'm sorry. Say again.
You mean November 4th? Because it's like.
Oh yes. Sorry, you're absolutely right. I have this thing. We are having a final.
Okay.
So the course has two normal.
The
course has. Sorry, it's just how Zoom works. Someone ends up speaking right when someone else was beginning to speak. So, thank you. Yes, November 4th. Thank you. I have this thing where sometimes the word in my head just isn't the word that comes out of my mouth. So our test is tentative. Our second test on chapters 5 through 8 is tentatively will be available to be taken around October the 4th. I did it again. November the 4th, and it'll work the same way. You'll have over the weekend to find the time to work on it. And the course is going, this will be the second normal test, and that will be in 2 weeks. And this test, it is a normal regular test. It'll be averaged with your previous test to create your test average for the class. And keep in mind the tests together make up 40% of your class grade. The final exam is different. That is going to be November. That will be available to be taken November 22nd through November 25th. That is the very last thing that all of your classes will be doing. And that final exam it'll count for the exam part of your grade, which is about 30% of your total class grade. And it'll be cumulative to the entire semester. Our second test coming up is only going to be on chapters 4 through 8. Sorry. Wow, I keep misspeaking. Test 2 will be on chapters 5 through 8. 1 through 4 were the first test. 5 through 8 are the second test. So in 2 weeks, we will open up that test, and we'll cover a few additional small topics after the conclusion of that test, because it's important for you to understand how light and sound and electricity works. So we will cover those additional topics, and they will just be factored. Some questions about them will be added into the final. Every course needs to have its own final exam, and so that final will be about everything for the entire semester, and that is scheduled as the last thing in your classes from December. Wow, I keep saying the wrong month today. Exams will be November 22nd through November 25th. Once exams wrap up, you go home for Thanksgiving, and then you stay there. That's the end of the semester. Did that address any questions or concerns that you had? Okay.
Did you say that the test was from the chapter 5 to 8?
Yes. So this coming test is just chapters 5 through 8. It's going to be about pressure, which was last week, and heat and thermodynamics this week and next week. So just that chunk, that core of it will be the second test. Then we will move on to some small additional topics and then exam review. We will have plenty of time to review for the exam, make sure we cover everything that will be on it. And I will, like I did with the first test, I'll be making some sample questions that you can work on for test 2 and also for the exam, so that you can use those to practice so we can go over them when we meet up. That is a lot of information about the calendar, basically. So any questions, concerns from you guys about the coming weeks or any of the assignments that are due anytime soon?
I don't have any right now, but you're gonna be available from like 1:30 to 4:30 for your questions about the homework and stuff.
Correct.
Okay. Yeah, so I might need some help with that. I'm kind of confused on 5 and 6 a little bit, but I kind of know what's going on.
Yes, I will absolutely be available. The lab times are when I will just be hopefully in this same meet room. Hopefully I can keep the same meet code. You can just hop back in whenever you have questions.
Just a reminder, this week's lab, when's that due again?
I didn't think we had a lab this week. Do we have a lab?
Yes, there is a lab for chapter 7, and it should have been in the email I sent out at the beginning of the week.
It probably was. I probably just missed it.
Okay, I can also email it to you directly if you would like. One sec. Wait, hang on. Sorry, I'm confused now. One sec, everybody. Got to check something. Okay, am I back? All right. School Wi-Fi has been glitchier than normal today, and I do not appreciate it. Okay, sorry about that. Any other questions before we move on to Chapter 7 today? You remember that you guys can chime in with any questions you have at absolutely any time, and that we will have the lab session in office hours this afternoon, where you can also jump back in anytime. So let us pick back up where we left off. We were talking about temperature last time, and we talked about the three separate units, measurements of temperature that we will be using in this class. Those scales are Fahrenheit, Celsius, and Kelvin. If you have your notes open to slide 10, and I'm just sharing that now. This shows the formulas for converting between Celsius and Fahrenheit, and then the formula for converting between Kelvin and Celsius. Now, let's talk a little bit about each unit. Fahrenheit is the first unit that was invented, and that's possibly why America still uses it, just because it was the first and we've been using it, so why change? Fahrenheit was invented by a man named Gabriel Fahrenheit, and for some reason, Gabe decided to make 212 degrees Fahrenheit the boiling point of water, and 32 degrees Fahrenheit the melting point of water. I don't know why. It seems like a very strange decision to make. And because those units seem kind of odd and they don't really, everything seems kind of strange and offset in the Fahrenheit scale, a different man named Anders Celsius came along a couple of decades later and invented the Celsius scale. And the Celsius scale was designed so that the freezing point is 0, the boiling point is 100. They're a nice even distance apart. Freezing point of 0 makes sense. And so Celsius became the official metric unit of temperature for a very long time because scientists really liked the fact that it was nice and sort of organized in tens of 10 like that. But we eventually decided to mathematically write down the fact that 0 Celsius is not the coldest temperature that exists. Things can get colder than just the point where water freezes. It doesn't happen often in South Carolina, but even here we have days where the temperature is below freezing. Like some days it gets down to 30, maybe 25 Fahrenheit. That is below the freezing point of water, which would be below 0 Celsius. Temperatures can exist lower than that point, meaning that even though you can have ice at 0 degrees Celsius, it has a certain amount of thermal energy at that temperature. And the fact that you can reduce its temperature further means that it has thermal energy and more of it can be removed. To make anything colder, you have to remove thermal energy from it. And so for ice to go from 0 Celsius to an even colder temperature, that means it must still have thermal energy inside of it that can be removed. And eventually we estimated what the absolute lowest temperature in the known universe could possibly be. And in Celsius, that temperature would be at negative 273 degrees Celsius. The equivalent in Fahrenheit is about 460 below, negative 460 Fahrenheit. These are the lowest temperatures that anything in existence can be. This represents the temperature where an object has no thermal energy left. At these temperatures, the lowest possible temperatures, all thermal energy has been extracted from an object and its molecules are no longer moving at all. It's the coldest that anything can ever be. And we named this temperature absolute 0. And a different scientist named, this wasn't his name, it was his title, Lord Kelvin. I believe the last name was Kelvin, and this person did have an official title. So Lord Kelvin came along and made a new temperature scale to reflect what the absolute lowest temperature is. So in the Kelvin scale, the three scales we've talked about are Fahrenheit, Celsius, and Kelvin. In the Kelvin scale, I'm actually going to backtrack to slide 9 really quickly. In the Kelvin scale, 0 Kelvin is absolute zero. 0 Kelvin is designed to be is made note of as the lowest possible temperature. Now, the Kelvin scale was based on the Celsius scale. If you increase in temperature by 1 Kelvin, you will also increase by 1 Celsius. So, to convert from Kelvin to Celsius, you simply add 273 to the Celsius temperature, and that will give you the Kelvin temperature. Notice I'm showing slide 9 now. Try to make it a little bit bigger. On slide 9, the freezing point of water is the lowest temperature listed in all three scales. That's 32 Fahrenheit, 0 Celsius, and 273 Kelvin. Absolute zero is the lowest possible temperature. That's 0 Kelvin and negative 273 Celsius. Meanwhile, 0 Celsius is positive 273 Kelvin. And to go from 0 Celsius to 100 Celsius, that's from freezing to boiling, you increase by 100 Celsius. From freezing to boiling in Kelvin, you also increase by 100 units. You go from 273 to 373. So Kelvin and Celsius are directly connected. They are designed to match one another in terms of whether or not the units increase by the same amount. Fahrenheit is sort of the odd man out because 1 Fahrenheit is like half a degree Celsius. So Kelvin and Celsius are by far the preferred scientific metric temperature units. But because Kelvin is a better representation of the thermal energy level of an object, we tend to prefer using Kelvin because 0 Kelvin tells us that there is 0 thermal energy, whereas 0 Celsius doesn't, because you can't get colder than 0 Celsius. As a reminder, these are the formulas for how to convert between these temperatures. And I'm actually skipping ahead real quick to slide 12. We're currently looking at slide 12. This is a sample question that I encourage you guys to try on your own to make sure that you can convert between the units yourselves. We have here listed 45 degrees Celsius, 45 degrees Fahrenheit, and 45 Kelvin. So it's the same number in every different scale. And I want you guys to, on your own, make sure that you can convert each of these into the other scales. I do want you to notice that I did not write degrees Kelvin. I'm not entirely sure why, if this was Lord Kelvin's decision or not, but we don't have degrees Kelvin. We only have Kelvin. If I scroll back up to slide 9 and we look at the temperature chart here, the Fahrenheit all has degree symbols, the Celsius all has degree symbols, but the Kelvin doesn't. You don't have degrees Kelvin. It's just Kelvin. Sometimes you can pluralize it to say Kelvins, but there's no degree symbol there. So on slide 12, the fact that degrees is missing is not a typo. That's intentional. So you guys, I ask you guys on your own time to make sure that you can correctly convert between these temperature scales, and to make sure you're doing it right. On slide 13, the answers to these problems are listed. So let's just kind of look at each temperature scale to get a sense of how hot or cold 45 is for each of them. 45 degrees Celsius is a very, very hot day. If you recall, 0 Celsius is freezing point of water. And for a sense of scale, 25 degrees Celsius is room temperature. So right now, you're probably feeling 25 degrees Celsius, which is about 75 degrees Fahrenheit. So 45 Celsius is hot. It translates to 113 Fahrenheit, which is the heat of some deserts. Meanwhile, 45 degrees Fahrenheit is actually a very, very cold temperature, because that's only 13 degrees Fahrenheit above freezing. 45 Fahrenheit translates to 7.2 Celsius. This is not quite freezing, but it is very cold. This might be the temperature of some autumn nights or winter days. And then 45 Kelvin is unfathomably cold. 45 Kelvin is negative 228 Celsius, negative 379 Fahrenheit. You will never feel a temperature that cold. If you were exposed to any temperature this cold, your body would probably instantly flash freeze and you'd become a statue. This is colder than any place that naturally occurs on Earth. Most parts of the universe don't even naturally get this cold. The only way that we've actually created or experimented with temperatures this low is by artificially creating them in an incredibly well-insulated lab setting. You will never experience a temperature near 45 Kelvin. I hope you don't. If you did, something would be horribly wrong. So these are the answers. Make sure that you can get these answers when you're converting through these temperatures. They just utilize the formulas listed here on slide 10. Now, what I'm showing right now is slide 11. Temperature is how we can most immediately measure the thermal energy level of our surroundings. It's the measure by which we detect how hot or cold something is. Now we know that the more thermal energy something has, the warmer it will be. The less thermal energy something has, the colder it will be. But temperature itself is not the absolute final measurement of how much thermal energy an object has. The example shown on slide 11 brings up the case of you have one coffee cup that is at a specific. Meanwhile, you have in the other picture 1,000 coffee cups at the same temperature. Even if this one coffee cup is at the same temperature as this 1,000 coffee cups, because there's more mass down here in the 1,000, there's going to be more thermal energy down here than up here. Temperature is a measure of the average thermal energy level of a particle in an object. If we were to take one coffee molecule out of the one cup and one coffee molecule out of the thousands of cups, just pick one particle at random. If the coffee was at the same temperature, those two particles would have the same amount of thermal energy. They'd be moving at the same speed. But in the 1,000 cups, there's just more particles that have the same amount of thermal energy. So there happens to be more thermal energy in the mass of cups because there's just more mass. There's more particles here that need energy for all of them to be at the same temperature. So temperature tells you the average thermal energy level, not the total thermal energy level. It's entirely possible for one object to have a higher temperature than the other, but have a total thermal energy level that is lower. Temperature is a guideline that we can use to find more information. Any questions so far from anybody? Okay. So, when you, with your hands, touch something hot, what you're feeling is thermal energy transferring into your body. This is the container that had my lunch in it before I ate it today. And I warmed it up in the microwave, and the microwave warms up the food using we talked about the three methods that thermal energy can transfer: conduction, convection, and radiation. Microwaves warm your food through radiation. They literally blast your food with microwave radiation to warm your food up. And when the food is warm, it has a very high temperature. It has a lot of thermal energy. If the food has a higher temperature than my hand and I touch it, then thermal energy will transfer from the food and into my hand. This happens based on temperature and not total thermal energy level. Because the particles that make up my hand at a specific speed, the particles that make up the food are moving at a specific speed. If the temperature for this object is higher and those particles are moving faster, that collide with my hand, energy will move into my hand in those collisions. Meanwhile, if I touch something colder than me, like my thermos of ice water, thermal energy will exit my hand and enter the colder object. Thermal energy always transfers from hot object to cold object. The process of thermal energy transferring is called heat. So the word heat actually refers to the process of thermal energy exchange. Heat doesn't mean thermal energy itself. Heat is a change in thermal energy. So when you feel heat, you feel thermal energy entering or exiting your body. Your nervous system doesn't have a built-in thermometer. When you touch something, you can't say to yourself, all right, my fingertips are telling me that this object is at 75 degrees Fahrenheit. You don't have a thermometer in your fingertips. All your nerve endings are designed to detect is the transfer of thermal energy. If heat leaves your body will register cold. It will detect that whatever you're touching is colder than you. It detects thermal energy leaving. If you're touching something hotter than you, your nerves can detect thermal energy entering you, and that's what you detect as the sensation of hot. You do not have a built-in thermostat. You can only tell if something is hotter or colder than you. So on a summer day, when you go outside and you feel heat, you are feeling thermal energy transferring into your body. And thermal energy is naturally always going to transfer from a higher temperature object to a lower temperature object until those two objects reach the same temperature. The point at which the objects are the same temperature is called thermal equilibrium. It's not the point where they have the same thermal energy level. It's the point where they're the same temperature. It's an important thing to note. Now, thermal energy itself is a form of energy, which means we are going to measure it in joules. Joules is our metric unit of thermal energy, so of energy itself. So that's what we're going to use for thermal energy. There is a second commonly used unit for energy called calories. And yes, this is the same kind of calories that is in your food. The calories listed on a food package tells you the energy stored inside of the food you're eating. Higher calorie food has more energy stored in it, and that energy is released and made available for you to use when the food breaks down and is digested. So calories is also a unit of energy, but we're going to mostly be using joules. We're going to mostly use joules in this class. Now, if you turn your attention to slide 17, we're going to talk about the next formula in this particular chapter. When two objects at different temperatures are interacting and heat is transferring between them, thermal energy will move from one to the other, and the temperature of the objects is going to change. This formula, the specific heat formula shown on slide 17, is the formula that tells us how a specific object's temperature is going to change. Now, there's some variables in this formula you have not seen before, so we're going to step through one at a time. Q is the variable for thermal energy. Any Q in a formula is going to represent some amount of thermal energy transferring into or out of an object. So Q represents heat added. It represents the flow of thermal energy. So you can consider Q to be the variable shorthand for thermal energy. Now, the M represents mass. This is the mass of whatever object you are looking at the temperature change in. And then delta T is the temperature change. So, to read this formula in full, when you add a specific amount of thermal energy to an object with a specific mass, its temperature will rise by a specific amount. Subsequently, you can remove thermal energy from an object with a certain mass, and its temperature will drop by a certain amount. There's a remaining variable here, this letter C, which I will explain momentarily. Frustratingly, I have to make a poorly timed trip to the bathroom. So what I advise you guys to do right now is first, while I'm formulate your questions about anything we've talked about so far. I also recommend that you go back and look at the temperature samples here and make sure you're able to convert correctly between these temperatures. Work on that, gather your questions. I'll be right back. Hello, everyone. Sorry about that. Okay. Any questions before we continue? Anything at all?
Where it says delta T is measured in degrees Celsius or Kelvin, would
Yes.
that also change the like if we measured it in one or the other, would that also change the like specific heat's final measurement?
It won't. It won't actually. And it's a good question. The reason for that is 1 degree Celsius and 1 Kelvin are the same size. So, as a sample, let's say that you increased an object from 25 degrees Celsius to 30 degrees Celsius. That's an increase of 5 degrees Celsius. Now, the equivalent to 25 degrees Celsius in Kelvin is going to be 298 Kelvin. And if we increase from this to the same temperature, okay. If we then convert 30 degrees Celsius into Kelvin, we will find that is 303 Kelvin, because all you do to convert from Celsius to Kelvin is add 237. So, in terms of the Celsius increase, we went up by 5 degrees Celsius. The Kelvin also increased by 5, because Kelvin and Celsius are the same size as one another. And so this formula specifically lists delta T, which means you will only ever plug a change in temperature in here. And the delta T for both Kelvin and Celsius is always going to be the same number. So for the sake of like canceling out when you're looking at units, like being when you're looking at units being multiplied and divided together and whether or not they will cancel, Celsius and Kelvin will cancel each other out in this sort of a hierarchy. So if you plugged in Celsius here and the specific heat said joules per Kelvin per kilogram, then those can be considered the same enough to cancel out. So when you are given a specific heat, if that specific heat is in terms of Kelvin or Celsius, it'll be the same number, and you can plug Kelvin or Celsius in for delta T, as long as this is Kelvin or Celsius, and this says Kelvin or Celsius. Either way, it'll cancel out fine. All the numbers will be the same. Does that answer your question, and are there any others?
Yes, sir. Thank you.
You're welcome. All right. Anything else? We mentioned C for a little bit in that, so we're going to explain that in a little further detail now. C is a new variable that is specific heat. Now, in this formula, you add a certain amount of thermal energy to something, and its temperature is going to change by a certain amount. But different objects will respond to the same amount of thermal energy in different ways. If an object has more mass, it'll take more thermal energy to make it warmer. So we factor that in with the mass term. The more mass you have, the lower the temperature increase will be for the same amount of thermal energy. But mass isn't the only way of describing an object. Two objects of the same amount of mass might themselves require different amounts of thermal energy for their temperatures to change. I want you to cast your mind back to a hot summer's day. Maybe you were going to the beach or the pool, someplace you were eventually going to end up in a body of water. Imagine going back to that day. You arrive at your destination, you get out of the car, your shoes are probably already off because you're going to just walk over and get in the water anyway. And you step out of the car and you put your foot down on the parking lot that you just entered. And the asphalt of that parking lot is usually very, very hot. Whenever you step onto pavement on bare feet, on a summer day, it's going to be hot. It's going to not be fun. So what do? You're on the hot pavement, which is basically just stone, and you jump off of the pavement as quickly as you can to try to get onto something like the grass. And the grass doesn't burn your feet as much. It's not as hot. But suspiciously, the grass and the pavement are both getting the same amount of daylight. Energy from the sun is coming in and striking them both. They're getting the same amount of energy from the sun. They're touching the same temperature air. So why does one feel hotter than the other? Why is one of them at a higher temperature than the other, even though they're getting the same amount of thermal energy? The reason comes down to the specific heat of whatever the object is made of. Every different type of substance, every different material, iron, aluminum, concrete, water, all have a different specific heat, which tells you how much thermal energy that specific substance needs in order to increase or decrease its temperature. Different materials have different specific heats. If you look at the table on slide 17, there's a table on this particular slide here that shows specific heats of various materials at normal atmospheric pressure. Some of them have a very low specific heat. Some of the lowest, I'm going to draw your attention primarily to the joules per kilogram degree Celsius column. And there's some very low specific heats on this table. Some of the lowest ones are lead, which is 128 joules per kilogram per degree Celsius. Mercury, silver, tin, cadmium, copper. The lowest ones on this table all tend to be things like metals. Metals tend to heat up very quickly. They don't need a whole lot of thermal energy to increase their temperature. Another example, when you get back into your car after it's been sitting out on a hot summer day, you get in your car, you sit down, you're touching the steering wheel, you're touching the console. Those materials are usually not very hot. You can usually touch the steering wheel when you get into the car, but when you reach over to grab the seat belt and you accidentally touch the metal part of the seat belt, that is usually scorching. It's made of metal. It has a lower specific heat. It will increase its temperature more from the same amount of thermal energy that everything else is getting. So the material that has one of the highest specific heats is water. Water has a very high specific heat. And the reason that the grass felt colder than the concrete is because grass is primarily made of water, as are you. Water has a very high specific heat, which means it takes a lot of energy to increase the temperature of water. It barely takes any energy to increase the temperature of metal, which is why the seatbelt metal heats up so fast. It's why the concrete heats up so fast, because most stones are metallic compounds. Rocks are made of metal for the most part. So the concrete, the metals, they all heat up very quickly, but water does not heat up as fast. This is why even on a hot summer day, jumping into the pool, the lake, the ocean, the water can still feel cold. The ocean receives a lot of thermal energy from the sun, but because the mass of the ocean is gigantic, and because water has a very high specific heat, that amount of thermal energy won't increase the ocean's temperature that much, which allows the ocean to stay cool. This fact, the fact that water has a very high specific heat capacity and does not change its temperature very easily, is one reason why life is possible on this planet. If water had a lower specific heat, the sun could boil the ocean, which would be a huge problem because nothing could live in the ocean and the atmosphere would be full of steam and everything would be terrible. Water having a uniquely high specific heat capacity is one of the things that makes life on this planet possible in the first place. Now, every single kind of object has its own unique specific heat, and kind of like all of the other concepts that have their own unique number attached to them, you're not going to have to memorize any of them. This table will be made available to you when you need it, or perhaps a problem will be about finding out what the specific heat of a particular object is by using this formula. You will always have all the information you need to you'll either be given specific heat or it'll be your job to find it using this formula. So, to review the formula in full again, you add a specific amount of thermal energy to an object based on that object's mass and its specific heat capacity. Its temperature will change by a specific amount. These are the factors that affect how an object's temperature is going to change in any given interaction. The unit for specific heat that we are going to use most of the time is joules per kilogram times degrees Celsius. So when you're looking at the column on that particular slide, you want to use numbers from the first column, the column labeled joules per kilogram per degree Celsius, not the column with calories in it. These numbers are the ones that you're going to want because we want to use kilograms for our mass and either degrees Celsius or Kelvin for our temperature. Any questions about this formula or the concept of specific heat? Okay. We're going to use this in a particular example. This example is the kind of work that scientists actually use this formula for. So if you turn with me to slide 18, a metallurgist, and that is the name for a scientist who specifically studies metals and their behaviors. A metallurgist heats an unknown sample that has a mass of 100 grams. Oops. So I'm going to start listing what we know and don't know. The mass of our sample, this marker is dying. We have a 100-gram sample of some metal. You don't know what kind of metal it is. A lab assistant just found it and brought it into your lab, and it's your job to figure out what kind of metal it is. Wait, hang on. Uh-oh. I'm sorry, guys. This is an older version of my notes of the slideshow where I left a piece of information out from this sample. I am very, very sorry. Yep, I made a mistake here. That's my bad. I left out a piece of information to the sample on slide 18. So we are going to revise the question somewhat. We're going to revise the question somewhat. I apologize for needing to make this change. This metallurgist has a 100-gram sample of a grayish metal. And let's just say that through trial and error in various processes, The metallurgist figures out that the metal in question is silver. So what a metallurgist will do is they'll undergo various testing on various objects in order to figure out what a sample is. Let's just say that this particular sample is 100 grams of silver, because I apologize for accidentally leaving that information out of the notes. And now that we know that it's silver, we can turn our attention to the specific heat table on this slide, and we can see that the specific heat of silver is 234 joules per kilogram degree Celsius. Now, the scientist, the sample begins at an initial temperature of 25 degrees Celsius, and the metallurgist is going to heat up this sample of metal until it approaches a final temperature of 800 Kelvin. And we are asked to figure out how much thermal energy, how much heat was transferred into this object to make this temperature change happen. So, we want thermal energy, we know the mass of the sample, we know the specific heat capacity of silver, and we know where its temperature began and ended. So we can start plugging in our variables. Here, whoops. Going to solve for Q. Going to solve for thermal energy level. It's equal to the mass of the sample, which is 100 grams. All of our formulas want kilograms, so let's convert that to 0.1 kilograms. Specific heat capacity of silver, 234. And now for the change in temperature. Delta anything is always final minus initial. So 800 Kelvin minus 25 degrees Celsius. Are we ready to proceed? We are not. These two temperature units are in different scales. We have Kelvin and Celsius. They need to match each other. You can use Kelvin or Celsius in this formula, but you can't use both at the same time. These two units have to match to tell us exactly how far apart the temperatures are. So we need to convert. I would recommend converting the Celsius to Kelvin. If for no other reason, then I know what 25 Celsius is in Kelvin. It's going to be 298. Now that these are the same unit, and we've converted our mass as well, we can solve for the thermal energy required to make this happen. Where's my calculator? So our final answer should be 11,746.8 joules, which is a lot. That's not an insignificant amount of energy.
Could you say that again?
The final answer?
Yes, sir.
Sure, and I will turn off presenting so that the screen is easier to see. So, our final answer should be 11,746.8 joules. We got that number from multiplying 0.1 for mass times 234 for C times our change in temperature, final minus initial. We have to make sure our temperature units match one another. We can use Celsius or Kelvin. We just need to make sure they both are the same. So 25 Celsius is 298 Kelvin. Multiply all that together to get 11,746.8 joules. Now, it is possible to basically do this sort of a problem in reverse. Say, for example, we knew how much thermal energy we added to the object, and we wanted to figure out what its specific heat was. So say we didn't actually know what metal this was. We didn't know its specific heat, but we knew that we could add a specific amount of thermal energy and we could observe the temperature change by a certain amount. Oftentimes, what a lot of scientists will do when they don't know what something is made of, they will add a specific amount of thermal energy, track its temperature change, and solve for the specific heat. And when you know the specific heat, you can then look at the table and figure out what material has that specific heat. So you can use this to identify things, which is what a lot of metallurgists do for a living. Any questions about any of these principles at all? Or about any of this math on the board? Okay. There's going to be one more concept in the Chapter 7 notes, and we're just going to cover it very quickly. If you turn to slide 19, there's a graph that I'm going to replicate on the board so that I can point to it and color a few things in. Okay. Now, we have talked about phases, the phases of matter, or the states of matter. Now, we know, in general, that when you heat something up, it will eventually go from solid to liquid, and if you keep heating it up, it will eventually go from liquid to gas. In order to do this, you have to increase the object's temperature by adding a specific amount of thermal energy to that object. But something interesting happens during the phase change itself. So the image that you can see on slide 19 is a graph, and it's a graph showing the x-axis is thermal energy added to an object. The vertical axis is the object's temperature. So, as the graph goes along this axis, you add more and more thermal energy to an object. As the thermal energy level rises, its temperature is going to start rising. That makes sense. The more thermal energy you add to something, the higher its temperature goes. But something interesting happens during the point where an object's phase changes, where its state begins to change. So what I'm filling in now I'm showing what parts of this graph represent each phase. So we're going to go through the graph one section at a time. Let's say that on this far edge of the graph, this origin represents a temperature of absolute zero and that the object has zero thermal energy in it. When you have no thermal energy, then your temperature is absolute zero. It's the coldest you'll ever be. So this point, the beginning, represents a zero for temperature in Kelvin and for thermal energy level total. Now, as you add thermal energy to a solid object at absolute zero, its temperature is going to start rising, which is what the slant on this graph represents. You increase thermal energy level, you increase the temperature, and the solid will increase in temperature from absolute zero up until you hit the point, the temperature at which that solid will start to melt. So if we were looking at a chunk of ice right now, this temperature here would represent the point of this temperature would represent 0 degrees Celsius, the point at which ice will begin to melt. So we've added thermal energy, we've increased the temperature, and now we're at the point where a phase change is about to start. But something curious happens during the phase change. Let me turn your attention to my thermos of ice water. This thermos has both ice and water in it. The contents of this thermos is 0 degrees Celsius. It is 0 degrees Celsius inside this thermos right now. And there is both water and ice in it at the same time. If the water is at 0 degrees Celsius, do you think would you expect it to immediately freeze entirely? If the ice is at 0 degrees Celsius, would you expect it to immediately completely melt? The answer to both of those questions is no. Phase changes take time. If you take a chunk of ice and set it out in the summer sun, it does not immediately begin melting as soon as it's exposed to. It does not completely melt. It doesn't immediately go from solid to entirely liquid just because it's in a warmer place. It takes time for that phase change to occur. So, to cause a phase change, you have to get a substance to the temperature where its phase will begin to change, and then you have to keep changing its thermal energy level while it stays at the same temperature. The ice will remain, if you were trying to melt the ice itself will remain at 0 degrees Celsius until it completely melts. Any ice that is still there will still be at 0 degrees Celsius until it becomes water. This point here represents where all of the ice has melted. It's now completely water, completely in the liquid state. And then once it's all liquid, any more thermal energy you add will increase the temperature of the water. So this piece here, that's a terrible red marker. That's better. This piece here represents adding in thermal energy to increase the temperature of the water. Once water exists by itself, its temperature will increase when you add thermal energy. But if ice is at 0 degrees and has begun melting, the ice won't get any warmer until it's done melting. Phase changes take place in their entirety at one specific temperature. And you should hope this to be the case, because if it didn't, then your ice water wouldn't stay at 0 degrees Celsius. Right now, the contents of this is at 0 Celsius because the ice won't become warmer than that until it's done melting completely. The same thing works in reverse. If you are trying to freeze water into ice, you have to get the water's temperature down to 0 by removing thermal energy from it. Then its temperature is going to stay at 0 as you keep removing thermal energy to freeze it.
So basically, while there's ice still in water, the water and the ice are at 0?
Yes.
Okay.
The rule here is phase changes always take place at a constant temperature. That's the thing I want you guys to take away, the practical sort of a life application here. Phase changes always take place at a constant temperature. Another example, when you get water up to 100 degrees Celsius and it starts to boil, we've added thermal energy to the water. It's now at 100 degrees Celsius, and it's started to boil. The water does not immediately completely turn into steam. It stays as 100 degrees Celsius water as it goes through the process of boiling. You want it to stay at the same temperature so that you can cook in it. As you add more thermal energy, the water will continue to evaporate. When you put on a pot of water to make your noodles, and it gets up to boiling, it will be evaporating the entire time, but because it takes time for the thermal energy to transfer in and to turn more of the water into steam, you will still have boiling 100 degrees Celsius water there the entire time. Which is good, because that's how we cook. Eventually, once you have added enough thermal energy to evaporate every single gram of water, then everything will be steam, and adding more thermal energy to the steam will make it warmer. So, the takeaways are, phase changes always happen at constant temperature, and all steam has more thermal energy in it than boiling water. Because to make it steam, you had to add a bunch of thermal energy, and then it started increasing in temperature to get even more thermal energy. So steam is hotter than boiling water. Steam burns are bad. Don't get steam burns. Just some practical advice that I hope never actually has to come up in your lives. But all gases have more thermal energy than their liquid counterparts by default. Those are the practical takeaways from this. Those are the things I want you to remember. The last slide in this notes is a couple of terms. The takeaways I want you to know from slide number 20 are the words endothermic and exothermic. An endothermic process has an object absorb heat from its surroundings, and an exothermic process has an object give heat off into its surroundings. So when an object is cooling down, it is giving its heat away to other objects. That would make a process exothermic. That technically means that freezing is an exothermic process, because when you freeze something, you take thermal energy away from it, it vents that thermal energy away, and so freezing is exothermic, and it warms the surroundings of the object being frozen. Meanwhile, melting is an endothermic process. It absorbs heat because that melting, it is absorbing heat into itself in order to make itself melt. In doing that, it cools the environment around it. When ice is in your hand, slowly melting, it is making your hand colder. So slides 19 and 20 are just these concepts that I want you to be familiar with. The formula on slide 17 and the conversions between different temperature formulas are what will make up the bulk of the math homework and the math questions on the homework and quiz this week. And with that, that is everything in chapter 7. This one was very concept driven, but we're going to use these concepts next week to talk about more thermodynamic and pressure-based systems. So we're reaching the end of the normal lecture period. Do you guys have any questions about anything at all before we break? Okay. As a reminder, I will be in this call from about 1:30 to 4:30, having office hours during our lab time. You jump in, ask any questions you have about any of the assignments. Right now, we're going to take a quick break. So I will stop the recording, and if you guys want to jump in starting at 1:30, please do. I'll be right back here. And until then, thank you all. And if I don't see you again, have a wonderful day. Oh, work on your Chapter 7 assignments. Sorry, Chip,
See ya.
question. Oh, see you.